Hello, everybody. Welcome to this session. I'm going to be kicking off the first talk of the session today. We're talking about SiFive intelligence and our VCIX interface. So excited today. You don't only get to hear from me. I'm Krste Asanovic, so I'm co-founder of SiFive, as well as current chief architect, also chair of the RISC V board and professor at UC Berkeley. As well as hear from me at the end, you'll hear from Cliff Young, who's he's from Google. He works on TPU architecture there. He'll be telling us some ideas about how to use things like this in future things. So let's talk about SiFive's Intelligence X280. So this is a product SiFive announced last year. It's been out for over a year. But recently, we did a bunch of refreshes to this product, a lot of improvements. It just came through this year. So we're happy to talk about it some more. So what is the Intelligence X280? So unlike our other cores, this one is really focused on wide vector throughput. And so it's a very efficient two-issue in order scalar CPU, 64-bit address width, with a complete vector unit on the side that matches the complete RISC V Vector 1.0 specification, so completely compatible. So it's a full applications processor, has full V support in the vector unit. And the vector unit in the X280 has 32 512-bit vector registers. So VLAN is 512 in the X280. And it can actually produce up to 512 bits of result per clock cycle, sustained in the LU. And when you use LMOL equal 8, as part of the RISC V standard vector spec, you can get up to 4K bits a vector. You chain together 8 vector registers in that case. You can do up to a 4K vector instruction operation in one instruction. So in addition to the standard RISC V vectors, we also added extensions for AI and ML. So there's a few SiFive custom extension instructions, which I'll talk about a little bit later. And one thing to point out, it's a very capable number cruncher, but it's also a full-blown applications processor that's compatible with the RVA22 profile, and so can run standard Linux as well as having this vector compute capability. Some of the recent upgrades from this year, we now expanded up to supporting 16 cores in a coherent multi-core configuration. And there's a high-performance memory system. So every core has private level 1, level 2 cache. And in the coherent configuration, you share a shared L3 cache, as well as various ports out to main memory. So performance numbers down there. Again, this is something we introduced a year ago, but we have a refresh with some new features and updates this year. So just to go over the extensions we added, if you just start with the RISC V scalar ISA and run small AI workload, this is one example we looked at. Moving from scalar to vector, you get a big improvement, as you'd expect. You know, these AI workloads are highly vectorizable, and we actually get a 24-time speed up by mapping the workload onto the vector instructions. But even from that point, when we added the new AI/ML instructions, which basically consist of some quantize instructions, matrix multiply instructions of various kinds, when we use those, we get a further 6x speed up. And so that means the vector unit is a pretty capable unit for doing smaller AI workloads, right? So it's not a ginormous AI accelerator, but it's quite capable in itself to run relatively small models at reasonable speed. Now, when we came out with the X280 last year, one of the surprises we had, well, first of all, it was very well received. So we were surprised that the uptake of X280 is a very popular core for us. And as we started engaging with customers and figuring out what were they doing with it, we realized that one of the popular use cases were really to put this next to an existing AI hardware accelerator. So they're using it as a companion to a more hardwired accelerator that they were really focusing on, right? So there's some very large engine that could do a lot of operations per cycle. And they're using the X280 kind of for housekeeping, but also to handle the compute operations at reasonable speed that they couldn't do on the fixed function accelerator, right? So typically, these accelerators have a few things they're very good at, the key kernels, but then there's other around those kernel compute you have to do that are difficult to do in a general way on the accelerator, so you move it over to the X280. So a lot of our customers are using the X280 in this companion core role, and so we dived in and started looking at that, and initially what they were doing is memory mapping their accelerator into the X280 space. The X280 was driving this through memory mapped interface. And customers saying, well, that kind of works, but it's for more efficiency, we'd like to have a much smoother coupling, lower latency between them. So we started talking with the customers and figuring out what's a way we can improve things. So we decided to add this vector coprocessor interface extension onto the X280. And so what this does is give you a direct path between the vector registers in the vector unit and the vector accelerator. So the custom instructions, so these are mapped into the custom instruction space in the RISC V ISA, and the customer can take our core, and those custom instructions will then appear on this interface along with data read and written from the vector registers. So now you can use this to add actually just instructions. If you just want to add custom instructions that look like new vector instructions, they can take multiple operands from the vector registers, write results back to the vector registers. Or you can have a larger, more stateful engine out there, in which case you're pushing and popping vector register data into that accelerator and back again. And in the X280, this interface is actually quite wide. So let's go into some more details. So again, just to see here, you see the difference. We're going from sort of order 100 cycles to get through the memory bus matrix. And now it's like sort of order 10 cycles round trip in and out of the vector registers through the accelerator. So big increase, big reduction in latency as well as a huge increase in bandwidth through this interface. So let's dive down in the details. So zooming in on one of the X280 cores. So you can see over there how the VCIX plugs into the vector register file. So the instruction stream on the X280 is fetching and decoding, executing RISC V instructions. When it encounters one of these coprocessor instructions, it will then launch those instruction bits out through the custom coprocessor interface, and also any accompanying data, vector data that goes along with that instruction. So those are read from the vector registers, and they're fully interlocked, hazard checked with the other vector instructions on the X280. So it's just like another instruction in the instruction stream, and fully synchronous with the X280 instruction stream. So you can send up to 1024 bits of data per clock cycle sustained to the accelerator and retrieve 512 bits per clock cycle sustained back into the vector register file. So the way to think about this is equivalent to, on the X280, when you do a widening floating point multiply add, you have a double width accumulator input and two single width product inputs. And each of those are 256 bits per cycle on the X280. So you have a total of 1K bit. That's where that's coming from. And coming back, you have a double width accumulator, which is 512 bits coming back as well. So this interface runs with the same data bandwidth as our widening multiply add instructions on the X280. Okay? But now you can put your own logic in that path. And if you're just adding your own custom instruction, you can just add the logic there, and the data comes out and comes back. Or if you're building a larger accelerator, the format allows you to push data out without waiting for a response. So you can keep pushing bundles of 1K bits per cycle out, and then later retrieve data at 512 bits per cycle coming back with a more decoupled interface to that coprocessor, if you wish, in the design. So again, this allows you to bring your own coprocessor into the X280 design, very tight coupling. It's right there in the same instruction stream, very wide data bandwidth, very low latency connection to that thing. And again, this is based on what we saw our customers were doing with the original X280, and this is a new feature we've added, the VCIX. So software is critical to doing anything, and with the X280, the great thing is we can leverage the great RISC V software ecosystem, but now we've added the vectors to that, RISC V standard vectors. And so there's a range of ways you can approach programming that vector unit. Everything from, you can go down to assembly code and hand-tune key kernels, write those in assembly code directly to the vector ISA. There's also the evolving intrinsic standard, where now you write your code at the C level using intrinsics that map down to those instructions. And in this case, what's happening is the compiler is taking care of things like register allocation and instruction scheduling for you, but you still have to break things down into the basic instruction types and kind of have an idea where you're going, but it definitely reduces the effort of getting good code out. Another thing we've done is a lot of our customers are moving from other architectures, and to help them make that, do that migration, we've added some tools. So one is called Recode, and what Recode will do is take ARM Neon intrinsic code, and with a change of the header file, that will now be recompiled to RISC V vector code. So you can take Neon intrinsic code, and it'll be compiled into RISC V vectors. And now this is not perfect efficiency, But for a lot of applications, what often you're trying to do is get most of the code up with reasonable efficiency quickly and correctly, and then later you'll go through and profile and tune the key kernels and map those natively down to RISC V Vector. So it's really a transition tool that helps customers migrate from other architectures into RISC V Vectors. So that's Recode. Finally, we have a lot of work on vectorizing compilers. So Alice Chan from SiFive is giving a talk here about that vectorizing technology. So I'll leave it, go see her talk on the LLVM auto vectorizer. But this basically will take C code, figure out automatically how to vectorize and map it to the vector unit. Now, the thing with auto vectorizer technology, it's not magic, and it will not do everything you want. And so sometimes you have to work with it, understand its quirks, and maybe restructure your code a little. But the benefit is then you have generic C code that anything could compile and run, but that with the right settings will auto vectorize well and map to the vector unit. And finally, a critical thing is having highly optimized libraries. So to really get the best performance, SiFive is providing kernels that have been hand-optimized, hand-tuned down to our microarchitectures to let you really wring the most out of it. So these are pre-existing libraries you can call to give you the basic linear algebra functions and functions for AI/ML training. And so those are made available from us, and they directly target. They've been designed and tuned for the X280 microarchitecture. So you see there's an evolving spectrum of how we get software across onto the X280 to support the product. Okay, so we came out the X280, a lot of uptake. We saw this one use companion code. We developed the VCIX, and we developed the software to help people work with that. We thought it'd be interesting to have Cliff come up and give his ideas about how this is a good thing to do and how it might be used in future accelerators. So Cliff, let me hang over.
Thanks, Krste. All right, next slide. So hi, I'm Cliff, and I'm from Google Research, and I wanted to talk about some of the awesome potential of these kinds of coprocessor interfaces and the way that they tie into the RISC V ecosystem, into vector processing, and the future of accelerators. In some ways, this is an age of accelerators. We are building general purpose cores in all the ways that we can, but Moore's law is stretching in various different ways, and things like TPUs and GPUs and also video compression accelerators are making a huge difference in how we do compute at data center scale. And so while I've shown a TPU-derived diagram, because that's my home ground and what I'm familiar with, you can put your accelerator here in the diagram. Let's talk about what goes into an accelerator, which is actually a computer. Many accelerators are Turing equivalent. They can compute arbitrary functions. They're just really, really good in the particular application-specific functionality you might care about, which for machine learning is often matrix multiplication, which you might build a systolic array for, but it could just as easily be something like a compressor or an encryptor or some other computationally intense activity that is of high value to a company. So they're still computers. They still do compute, like arithmetic logic unit sorts of things. They still do memory, and they still do networking. They still have to talk to the rest of the world to be useful to us. Those three categories haven't changed. And so if you're building a new accelerator, you have to invest in all those to build a working system. You can't neglect them, or your machine can't talk to the rest of the world, or it's kind of fundamentally hobbled in various different ways. But if you zoom in a little bit, particularly in some of the accelerated examples, not all of this has to be built from the ground up. In particular, for the case of, say, TPUs, the interconnect and the systolic array unit feel like the sorts of things where there's a particular specialization or competence in how we build something like a TPU. And again, in another accelerator, do you necessarily want to build everything else? Do you want to build the same vector memory? Do you want to build a sequencer or a decoder or a cache memory system or the way to talk to PCI Express? All of those pieces that go into building a computer are things that you might not necessarily have to build yourself. So wouldn't it be better if you could focus your design team down on the things that are the sources of your competitive advantage and let somebody else who's an expert in the more general processing kinds of things provide that kind of functionality? So I think there's a potential in all of the accelerator space for that kind of nice division of labor. So VCIX, I think Krste pronounced it VCIX. I've been calling it VCIX for short. We could have a marketing debate about the proper way to produce it. Is a huge help here, where suppose you are considering exploring a new kind of accelerator, should you build it from scratch? Like I guess we did for TPU V1 9 years ago because there weren't really good alternatives. RISC V was still very much academic, not commercial. It was hard to open up a general purpose core with an existing software ecosystem and use it. Now it's much easier. So why reinvent things that we can do already very well? So start with a RISC V base core. Go vector, because vector machines have wide paths to memory, and a bunch of the acceleration value is in that wide path to memory. Get it into the core for processing. Use RVV extensions where you can, which is future-proof, portable, backwards compatible, and so forth. Use the toolchain. It's really great to be able to program in C or C++ or Python or R or whatever it is that the general purpose ecosystem wants to program in, rather than, again, having to build some specific software functionality for your specific accelerator and having those two be bound together. The VCIX interface, if you dive into the details behind the hardware that Krste described, has a really nice push-pop kind of interface to it. I don't think VCIX is the first. If I remember correctly, other coprocessor interfaces have had that kind of slightly asynchronous push-pop-like nature to them. And there's a division of labor there where you, what happens to the things after they're pushed or popped to the coprocessor and they come back is not necessarily managed or tracked by the base core. Instead, the base core can focus on being a great base core and building a vector memory system and compute unit, and the coprocessor or accelerator piece can focus on its particular functionality. And I guess Krste already alluded to the tighter coupling. Of course, you could build a bunch of this stuff to go through the memory system. And then, as he said in his slide, there's maybe hundreds of cycles to store something from a general purpose CPU and then fish it back out of your cache memory hierarchy. That's known good. That's how our systems on chips work today. And so that's not so hard. I think going back to the engineering costs, though, if I have to build something which goes through the memory system, then I have to build my own memory system. I have to build my own caches, which might duplicate the caches that exist in the base core. And I have to worry about coherence protocols. And again, all of that stuff, it seems much nicer to me to have access at the register level and be able to leverage what's already been built and is known to be good. And I'll tell maybe one more story about programming. In general, accelerators turn out to be hard to program, or at least the first one is hard to program. This is a continual issue for us in all of the accelerator space. All the weird machines that I've worked on have been a little touchy. In particular, I sometimes tell a story about on the first TPU, there's no mem copy, right? How do you got a chunk of memory here and you want to move it over there. How do you mem copy it? And the answer is you write a matrix multiplication routine with an identity matrix value and an identity function to do the mem copy, which is like a terrible abuse of your beautiful accelerator, like praying the size of a planet and you're using it to mem copy. But it's the only functionality that's there, and so you make do. I had to write that stuff myself. If you have a hybridized RISC V core with a vector memory system and all the compilations and libraries and so forth along with your accelerator, then memcopy's there. Like I had this lovely experience a few months ago, I think actually before the last time we gave this talk, where I just dropped memcopy into my code and the scalar core part of it presumably dispatched and did the memcopy because it was a tuned library and somebody had possibly even put the tuning into the library to use vector loads and stores behind my back. It was known good code, just like we on general purpose computers are used to using. Just call memcopy and do the right thing. And so I didn't have to write an on-accelerator version of memcopy. That seems like a really nice, again, savings of labor, both in the hardware design part and the software design part. And so I feel like this lets us get closer to that possibly El Dorado vision of an accelerator that might be easier to program. So I think there's huge potential, regardless of whether you're doing matrix multiplications or accelerating some other field. If there's something of high value to you and there's some weird kernel that you gotta squeeze special purpose hardware in to do it, you don't necessarily want everything to be on that special purpose hardware. You'd much rather have what I think I call a base core and Krste calls a companion core to share the work with and to interface much more cleanly with the general purpose ecosystem. So I think that was it for my slides. So shall we take questions, Krste?
Have you at Google already integrated one of your accelerators with the SiFive processor?
So the question was, have we already integrated with a SiFive processor? I'm in Google Research, so we have exploratory things that we're working with, but probably the question you want to know about is like, what is future production like? And we don't make disclosures about future production plans, I'm sorry to say.
So I have the impression from your description, when you think about accelerators next to a processor, a lot of times these accelerators, especially if they're fixed function accelerators in hardware, you know, they may have their own control flow. They likely have their own control flow. And is the takeaway from what you're describing here is that because of the mechanism that you're using to connect this accelerator into the processor, so you're giving the accelerator direct access to the vector registers, somehow those vector registers have to be scheduled and controlled and access synchronized and so forth. But the problem statements, your very last bullet on your last slide was a simple programming model, which I think means you're taking the control flow out of the accelerator and you're letting the compiler actually schedule that as if those things are basically mapped to the instruction space. Is that the right way of thinking of what you're describing here?
I think overall, yes, that's part of the potential. Some of my previous accelerator work has involved what I call formation flying, where you have a general purpose CPU core doing a task to feed the accelerator, and the accelerator with its own control unit and instruction sequencer, and they really have to fly together so that when the CPU pushes something in, the accelerator is ready to pick it up and so forth. That's kind of weird from a source code perspective. So this approach has the possibility that there's kind of one control stream. But there was another connotation in what you said about scheduling exactly to the accelerator that is not true in this interface. The push-pop interface actually gives you a great degree of decoupling between the coprocessor piece and the base core piece. And so Krste's great compilers and vectorization code will work fine on the base core piece, and they can treat the push-pop interface as something of a black box where you still have to manage the latency of whatever it is that you're doing in the coprocessor. But the push-pop interface lets you not necessarily fine-grained schedule about like the weird accelerator has to drop things in exactly this cycle back to the base core. There's a little bit of slack there built into the architecture, which is actually a nice, again, division of labor.
Yep, thank you.
Don't have a watch on. I think we're getting really close to time, so. Okay.
2048 pins? And how do you get the connection between the accelerator and the 280?
Who's the question to?
Pick.
Your PD team. This is your PD team.
Huh?
Your physical design team has to cope with all those pins.
Same die?
Yeah, this is,
Okay.
These are, you know, like this big.
Yeah.
tiny.
It's a die. It's on die. It's not
Yes.
two dies.
This is, you know, the X280 soft IP. Right.
Metal is great these days.
Okay, more questions? Okay, thanks.